Thank you for joining. So my name is Fatih, as you mentioned, and I work for Ericsson based in Stockholm, Sweden. And I work in open source 100%. So whatever I do is done out in the open.
Hello. So I am Yolanda from Red Hat. I work as an NFV partner engineer, so my main goal is to help Red Hat partners to deploy OpenStack, but also consume the latest NFV features. And especially, I'm involved on what is deployment, operations, and CI.
Hello, my name is Markos. I work for SUSE. I'm in the network team, and whenever I'm not working on some networking features for the enterprise products, I spend my time in OPNFV and the XCI project.
So today we will talk about the initiative which is named Cross-Community CI, which aims to bring different open source components together, integrate them and test them to make things faster. And this is actually a slight version of the yesterday's tutorial session. So hopefully this will clarify some of the questions you might have from yesterday. So I don't know how much you know about network functions virtualization, but here is a quick description of what it is. So today's networks are built using specialized hardware, specialized operating systems, specialized software, and it's basically dedicated resources are used for providing network functions, which we can call them physical network functions. And it is pretty slow to change how the networks are rolled out or how the new services are introduced. Based on this type of use cases, this network functions virtualization concept was brought up by XCI NFV, and it basically aims to replace how the networks are built by changing from special hardware to commercial off-the-shelf hardware, and from specialized operating systems to Linux, to enable faster innovation, faster introduction of new services and applications, and bring things faster to end users by ensuring that all these different layers, like hardware, software layers, are standardized, and applications can be brought in much faster than how it is today. And based on these concepts, XCI came up with this NFV architecture a couple of years ago to standardize how this can be done, how the networks can be transformed, and cloud or virtualization concepts can be applied to networks. And since standards work take some time to become reality, in parallel to this, about 3 years ago, this open source project was established around 2014, September, to do things by using open source components to make NFV transformation happen faster, in parallel to standards work. So standards bodies, they come up with standards, and OPNFV and other open source projects implement those things to see if those concepts or standards are applicable in real life. And yeah, it says OPNFV is career-grade, integrated open source platform to accelerate the introduction of NFV products and services, which is a textbook or website description of it. But it's actually, in short, OPNFV is a system integration and testing project done in open source, because it is very challenging to bring all these different components together, integrate them, and test them to see what works, what doesn't. And it's basically, OPNFV is a midstream project, which means that we consume all these different components from different upstream open source communities like OpenStack, Kubernetes, ONAP, OpenDaylight, ONOS, KVM, OVS, all these logos you see on the screen, and some more. And we bring different components, and we create different combinations of features to see, okay, we have OpenStack that is Virtual Infrastructure Manager. We put OpenDaylight for SDN controller, and we put FIDO for data plane acceleration. Do they work together? Okay, they didn't work. What to do? We go back to upstream projects, communities, and report these findings and tell them, okay, we put these things together and test them from telco point of view, and things didn't work. We should fix these things. And then OPNFV community and other communities directly work in those components and fix things there. So it's basically upstream nature of OPNFV. We fix everything in upstream projects, whichever they are. And the downstream nature is basically pulling those components back to OPNFV and testing again to see what we fixed, really fixed the problem we have or a new feature we introduce, does it really work? It's basically midstream. We both implement things, but directly in upstream also we bring things to downstream. We obviously not just bug fixes, but enhancements of existing features or creating new features in upstream components that is in the scope of OPNFV. And this gives you many different combinations. I think our current release will have more than 50 combinations. So you can have OpenStack underneath or Kubernetes. You can put 3-4 different SDN controllers. You can put some more on top of it, and you have exponential growth of different combinations. For example, we have 3 distros in OPNFV, Ubuntu, CentOS, and OpenSUSE. We first provision our machines with one of these operating systems, and then we need to bring virtual infrastructure manager, which could be either OpenStack or Kubernetes. Once we do that, we put some SDN controller on it, OpenDaylight, ONOS, OpenContrail, or Calico in Kubernetes case. And we enable some additional features we developed either in OpenDaylight or OpenStack to test that feature with this integrated platform. And then finally, we run some functional testing and performance testing against this platform to see, okay, this functionality doesn't work, find where the fault is, fix it, and try it again. And then we run some performance testing to see if it really fulfills the performance needs from telco point of view. And these are just subset of the components or features we are showing here. We, as I said, like more than 50 different combinations of things we have there. And this obviously can't be done manually. You can't put things together manually, more than 50 different things. And we have CI in place to support this. And today's talk is actually how this thing is done. Like, okay, we have the CI and we work upstream, but how we are really working. So first, you have an idea, you come to OPNFV with some other people, and you basically say, okay, we have to fix this thing. We have to bring new feature to OpenStack, for example. Once you have that team there, the project created in OPNFV, you write these requirements in OPNFV. And once the project team agrees in OPNFV, you go back to relevant communities, OpenStack or OpenDaylight, and write your blueprint there. And if OpenStack community accepts that blueprint, for example, Neutron project, you go and implement that fix there. And that fix gets tested by OpenStack CI and in the end released by OpenStack CI. And then OPNFV pulls that back into OPNFV CI to test if what we developed really works. And OPNFV uses stable releases of upstream components. Basically, our current release uses Okata, OpenStack Okata, and OpenDaylight Carbon. And the next release will use OpenStack Pike and OpenDaylight Oxygen, for example, which means that it takes at least 6 months for our contributions coming back to OPNFV. We test it, it adds a couple of more months on top of it, and then this essentially brings the overall feedback time to a year, which is very slow. Because we fix something, we find a fault with it in a year's time, we go back to OpenStack community and they say, it's in Okata, we are now in Queens. Come and fix that in Queens. But that thing is not there anymore. We are already pretty late. So we kind of lose the essence of CI and we lose the value we can add to this ecosystem. And this basically brings these problems, like we are very slow. Yeah, we do our best and we integrate these things as an open community effort, but we believe we can be faster than today. So we can provide this feedback when they matter to upstream communities. If we find faults today and report them tomorrow, I'm sure someone will fix them. But if we find faults today and report them in a year's time, we might not be able to get anyone listen as even. And also we always try to catch up. We are at least one release behind of all these projects. We have to be going a bit more aggressively against master branch and try to pull master branches into OPNFV and integrate the latest versions of all these components to find if the latest versions work fine or not. Another thing is that the quality and predictability is a bit unknown for OPNFV because we are at least a release behind and we are continuously doing uplifts of new versions when upstream communities release new versions. And that takes our quality very down, because everything stops working when we uplift from Newton to Okata, Okata to Pike. And it's basically, you take the quality down, you try to build the quality up again, and then you try to release. And this is like a loop which is very challenging to work with. If we move towards master, then we will try to keep things working at all times, which is basically continuous delivery. So we must ensure that upstream communities work in continuous delivery model, so we can apply continuous integration to OPNFV. Based on these findings, we came up with this initiative, which is called cross-community CI. You can think this like OpenStack third-party CI. You have different companies there hooking into OpenStack, get it. When someone sends a patch to Nova, for example, the company CI start running and testing those patches in their own labs. In OPNFV's case, we do this for all the communities we work with, not just with OpenStack, but OpenDaylight, Fido, and ONUP. And we are including even more communities to provide this type of service to them, basically becoming a CI machine for all these different communities for ecosystem, and providing this service from telco point of view. Because OpenStack tests things from OpenStack perspective, OpenDaylight tests them from OpenDaylight perspective, and someone needs to test this integrated platform. That is where we step in and run this type of CI. And this is the basic flow, just showing a few of the pipelines we have. Obviously, pulling down master and integrating them and testing them is valuable, but we can do even better than that, and we can prevent false slipping to master branch. We do that by running patch set verification jobs against upstream projects. And if you send a patch to Glance or Keystone, we should be able to catch that fault right at that moment, rather than trying that after it gets to master branch. Okay, we caught some failures, and we got new patches fixing those failures, and they get merged. And then we need to bring those master versions back to OPNFV, so we can combine these features or components together and create the integrated platform, which is what we call periodic jobs. And we continuously chase upstream master branches. Once we find working versions of those things, and we pin those versions and make it available to users, and further CI loops we have in XCI, which is daily and weekly, running more extensive testing. This essentially increases in our confidence in the integrated platform. And if we put developer here, this developer works with two communities, and basically we try to provide feedback using these combined features. And once the features get merged, we run daily tests and weekly tests, basically cutting the feedback time from a year to, in worst case, week times, and making things even faster. And we need some tooling for this purpose, which Yolanda will talk about.
Okay, so one of the objectives that we had when building this set of tooling is to be able to reuse the same set of tools that we were using at OpenStack Infra. So I'm core of OpenStack Infra there, and I'm also a committer on OPNFV CI, so that's what we tried to do, to just reshare the same tool and don't invent anything new. So how did we start to choose that? So some time in the past, I was working on Infra, and we were working on a project that was called Infra Cloud. So I'm not sure if some of you are familiar with that. So we were using some hardware that companies donated to Infra, and then we decided to deploy an OpenStack Cloud there to run the test on Nodepool. So we started on this effort, and we were choosing like two different toolings. We were choosing Bifrost for all the hardware provisioning, and then we were using the Puppet Infra Cloud, that it was like a small installer based on Puppet modules to deploy a very simple but functional cloud to be able to just deploy, attach to Nodepool, and run the test there. We had it running, and it is now currently running on Infra and is passing tests there. And then I started also to collaborate with OPNFV CI. I was talking with Fatih, with Markos, and so we decided to share efforts. We started to do the same, reuse the same structure, the same tooling on OPNFV. So we started working on that, and in the summit of Barcelona, we had a proof of concept based on that, but applied to OPNFV CI. We're using Bifrost and Puppet Infra Cloud. But then we discovered that this was not enough, because Puppet Infra Cloud was very thought for infra, and it was very limited for our use case. So for example, we don't have HA on Puppet Infra Cloud. We also couldn't deploy from master. We would have to pin to some stable versions. Also, we didn't have the ability to deploy all OpenStack components, because it was very focused to infra, so we could only deploy Nova, Keystone, just the basic things. Then we were thinking on choosing another installers, so we decided to use OpenStack Ansible for that, because it was OpenStack, it was upstream, contributed by several communities, several companies as well, and it had the features that we really wanted. You can deploy from master, you can pin patches, so you have your own code, you can just pin the version of the patch that you are using, you can test it. Also, you are able to deploy all the OpenStack components that you need, because it's very easy to contribute. You can create new roles to deploy new OpenStack components. So that's why we ended choosing Bifrost and OpenStack Ansible, and it's now the base tooling for XCI. Okay? Going to talk a bit about Bifrost. So Bifrost is just Ironic. It's a set of Ansible playbooks that allows you to deploy Ironic in a standalone way. So instead of having to deploy the whole OpenStack components to just get the hardware provisioning working, you have a set of Ansible playbooks that just install Ironic there on your server. You enroll the nodes there, and you can have hardware provisioning on those. Okay. It's supporting major distros, so it supports SUSE, CentOS, and Ubuntu as well. So you can install Bifrost on these platforms, and you can deploy these operating systems as well. And it's really easy to use. It's Ansible-based, so it's a set. You just need to run some playbooks. So you install it, you create some inventory, a JSON file that you will do the same as Ironic. You install, you add the nodes, enroll them, so it gets computed in the Ironic database, and then you can just start deploying the machines. So what's the status of that? Bifrost is really solid. It's really being used everywhere. Lots of companies. We have been using that regularly for our CI in OpenFV. We run actually as a third party for Bifrost. So every patch that arrives on OpenStack Bifrost in upstream, we run the third party CI on our site in OpenFV. So it has been really useful, because it allows us to just test Bifrost on the different environments and the different situations that were not covered by the upstream testing. It helped in covering so many bugs. It helped debugging with SUSE and CentOS integration. So it was really very good for that. And as I thought, it's being used daily to deploy all the nodes, really for our CI. Okay, now I'm going to show a bit how it works. So first of all, you need to run a playbook just to install Bifrost. You can run it on a jump host or VM. So it will install everything, and you will end with a working Ironic. You will have access to all the Ironic commands as well. Second thing you need to do is you need to create an environment file, so an inventory file. So it is just a JSON file or a YAML file that you just put the data of your servers, I mean the IP address, the way to connect, if it's SSH or IPMI, the credentials, and then you just enroll the nodes with that. Yeah, I'm not sure. Yeah, it's okay. You export the path of your inventory there, and then you execute the enroll playbook. So this will do, if you are familiar with Ironic, you will see that it's the same behavior. It will add all your nodes into Ironic database. And then you can see that you have it with the Ironic basic commands there. And then second steps is just to execute the deployment command. So it will take the Ironic nodes that are listed in your database, and it will just do the deployment. So what means the deployment? Bifrost will do several things. So it will install the operating system that you choose. You can just specify the image that you want deployed on your servers. You can customize the image with any content that you want to have there. It is also going to configure a basic network for you. So you will define the interfaces that you want to have configured. I mean, the kind of integration that you want to have as well. And it will also create some SSH keys. It will just will copy some SSH keys into your server. So after the deployment is done, you will have the nodes working for you. Okay, and it will take some time, and after that you will have it ready. it will have like the basic operating system configured and ready to deploy OpenStack on top. Okay? And then the second step after we have the deployment is that we deploy, and after we have all the nodes deployed properly, we will run OpenStack Ansible to deploy OpenStack on top. That Markos will talk.
Yeah. So as Yolanda said, the first step is to create the environment where we install OpenStack on. So once the machines are ready, either virtual machines or bare metal, then it's time to install the OpenStack Cloud. For that, we use the tool, it's called OpenStack Ansible. So this is being developed by Rackspace, and now it's an OpenStack project. The thing about the OpenStack Ansible is that all the OpenStack services are being installed in containers, in LXC containers. So in the end, you end up with having Nova in a container, Neutron in a container, Heat in a container, everything is in a container, which makes it easy to scale out if you just create another container. And it's very easy to, if you want to redeploy one of the components, you just destroy the container, run the playbook again, and, the service being redeployed very easily. So as before, like Bifrost, we support all 3 distributions. Basically, there are 2 ways you can use the OpenStack Ansible. The first one is if you are a developer, you can the way OpenStack Ansible is developed is it's a very modular. For example, every OpenStack component is a different Ansible role. I'm not sure if you are very familiar with Ansible, but a role is is a set of playbooks designed to do very specific things. For example, the Neutron role is responsible for deploying Neutron, and that's it. So if you are a Neutron developer, you can just clone the OpenStack Ansible role, and then you can just test your Neutron patch against the OpenStack deployment. There are tools there. For example, there is a Vagrant environment. You just spin up a virtual machine, and your Neutron patches are instantly being deployed in an OpenStack environment within a few minutes. And if you make a change and you run the playbook again, then your new change is also applied to the OpenStack environment. So that if you're a developer, it's very easy to try your patches on a real OpenStack platform without having to install one by yourself. The second way to use the OpenStack Ansible, if you are an operator, this is basically a proper way to install OpenStack Cloud, compared to, for example, DevStack, right? So this is whereas you can use it as a developer, but as an operator, you can, have a real deployment based on Ansible, and that's why we chose it for the XCI, because we support, very limited environments, like having an OpenStack Cloud installed in a single virtual machine, but we also want to have deployments, XCI deployments with 6 nodes. So we want to do it properly, and one way to do that is to use the OpenStack Ansible. Yeah, that's it for me. Any questions?
Any questions?
Thank you.
No questions? Well, it's too many things in such a short time, but we have all the documentation available. I think the slides will be available on the site somewhere. Yeah, and yeah.
Yeah, I have one. You mentioned that you are not pulling the upstream things to your CI system. Are there any plans to push feedback to upstream? Okay, now Fatih.
Yeah, we actually do that for Bifrost, for example. We hook into OpenStack Gerrit, and when a Bifrost patch comes in, we start jobs in OPNFV CI, and we report back to OpenStack Gerrit directly to patch, saying, okay, OPNFV CI started running patch set verification. And once the job is complete, we report the status back saying success or failure, and we provide the logs and everything. So upstream developer can take a look at the logs and fix the issue and amend the patch and get a new run. So we directly report the upstream Gerrits. We don't keep the feedback to OPNFV only. So if you are OpenDaylight, we report to OpenDaylight in that case. So.
Yeah. Okay. So this example Bifrost, that's OpenStack.
Yeah. Yeah.
Yeah. But how about OpenDaylight?
Yeah. Yeah, for example, OpenDaylight has networked project. We push feedback to networked patches directly in OpenDaylight Git. So it's like whichever project we are running CI for, we push feedback back to that project. So they can get the logs and everything directly from their Git rather than asking us. Yeah.
OpenStack Ansible, I think I read on the website that it was not production ready to deploy on CentOS, and is that true? Or
So the official upstream status is that only the Ubuntu job is voting, right? CentOS and OpenSUSE are non-voting jobs, even though we test them as well. In real life, I know there are deployments based on CentOS and Ubuntu and OpenSUSE, right? They're out there. They're just not voting jobs in OpenSUSE yet, in OpenStack yet. The reason for that is that we have in the infra team, there is a limit on how much time each jobs can take, and CentOS and OpenSUSE take longer than the limit, so that's why we cannot have them voting. We need to, improve them a little bit to achieve that time limit, and then we can start mark them as voting.